They stood on the observation platform at Schweinfurt, watching the formations pass overhead at 25,000 feet. It was October 14th, 1943, and Oberst Friedrich Lang had seen bomber formations before. He had watched the RAF night raids, had studied the damage patterns, had written reports on British tactics. But this was different. These were American B-17 seconds flying in broad daylight, in tight formations that looked like they had been drawn with a ruler against the autumn sky. What disturbed Lang was not that they came in daylight. The Luftwaffe had promised that daylight bombers would be shot down in such numbers that the Americans would abandon the tactic within weeks. What disturbed him was the precision. He watched through his field glasses as the lead formation opened its bomb bay doors. The bombs fell in a pattern so tight, so deliberate, that it looked like someone had simply poured them from a bucket directly onto the ball-bearing factories below. The explosions walked across the Kugelfischer plant with mechanical precision, not scattered across the city, not randomly distributed in the general area of the target. The bombs struck the factory complex itself, building after building, with an accuracy that Lang had been told was impossible at that altitude. He lowered his field glasses and looked at the young Luftwaffe captain beside him. The captain was still watching the sky, his mouth slightly open. "They told us," the captain said quietly, "that precision bombing from 5 miles up was propaganda, that it couldn't be done." Lang said nothing. He had been told the same thing. Everyone had been told the same thing. The doctrine was clear. Daylight bombing at high altitude meant the bombers would be vulnerable to fighters, and even if they survived to reach their targets, they would never achieve the accuracy needed to destroy specific industrial facilities. They would drop their bombs somewhere in the general vicinity and hope for the best. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But the fires burning below told a different story. The Kugelfischer plant, which produced nearly half of Germany's ball bearings, was being systematically destroyed by bombs dropped from an altitude where the bombardiers should barely be able to identify the city, let alone specific buildings within a factory complex. Lang had been an artillery officer in the First World War. He understood accuracy. He understood the relationship between distance and precision. At 5 miles, even the best artillery observer with the most carefully calibrated guns would be fortunate to put shells within a quarter mile of an intended target. These Americans were putting bombs within yards. The captain pointed to another formation approaching from the west. "The fighters got maybe 30 of them on the way in," he said. "Hauptmann, Wick's group caught them over Luxembourg. But look at them. They're still flying formation. They're still coming." Lang counted the aircraft in the nearest combat box. 18 B-17 seconds, flying so close together their wingtips seemed almost to touch. The formation discipline was extraordinary. Even under fighter attack, even with flak bursting around them, they held their positions with a rigidity that suggested something more than just training. He watched as the second wave began its bomb run. The aircraft seemed to pause in the sky for a moment, suspended, and then the bombs fell again. Another tight pattern, another cluster of explosions walking across the VKF ball-bearing plant. "How?" the captain asked. "How are they doing this?" Lang didn't answer because he didn't know, but he understood that something fundamental had changed in the nature of strategic bombing. The Americans had solved a problem that German engineers had declared unsolvable. They had found a way to bomb with precision from altitudes where fighters were less effective and flak was less accurate. And if they could do this to Schweinfurt, they could do it to any city in Germany. The confidence that Lang and thousands of other Wehrmacht officers shared in October 1943 was not baseless optimism. It was built on 3 years of combat experience, on careful study of British bombing campaigns, and on fundamental principles of military aviation that had been proven again and again since the beginning of the war. The Battle of Britain had taught clear lessons. Daylight bombing without fighter escort was suicide. The RAF had tried it in the summer of 1940, sending formations of Wellington and Blenheim bombers against German targets in occupied France and the Low Countries. The Luftwaffe's Bf-109 fighters had torn them apart. Losses sometimes exceeded 50% on a single mission. The RAF learned quickly and shifted to night bombing, accepting reduced accuracy in exchange for survival. The Germans had learned the same lesson from the opposite perspective. Their own daylight raids against British cities in 1940 had been devastatingly expensive once they pushed beyond the range of fighter escort. The Luftwaffe's bomber force never recovered from those losses. Both sides reached the same conclusion. Modern fighters made daylight strategic bombing impractical. This wasn't just tactical observation. It was supported by the mathematics of aerial combat. A bomber, no matter how heavily armed, was fundamentally a platform designed to carry explosives to a target. It was large, relatively slow, and had to fly straight and level during the bomb run. A fighter was designed for one purpose: to destroy other aircraft. It was faster, more maneuverable, and could choose when and where to engage. German fighter tactics had been refined through years of combat. The standard attack profile involved approaching from the front, where the bomber's defensive armament was weakest, closing to within 200 yards, and firing a concentrated burst from cannon and machine guns. A single Bf-109 pilot, properly trained and aggressive, could destroy a heavy bomber in one pass. A group of 30 fighters could devastate a bomber formation in minutes. The Americans knew this. Their own pre-war doctrine, developed by theorists at the Air Corps Tactical School at Maxwell Field in Alabama, had emphasized strategic bombing. But even the most optimistic American planners understood that bomber formations would need fighter escort to survive. The problem was that no fighter in 1940 had the range to escort bombers deep into German territory, so the Germans waited with confidence. When the Americans began arriving in England in 1942, building up the 8th Air Force, Luftwaffe intelligence officers studied the aircraft with interest. The B-17 Flying Fortress was impressive. It was large, carrying a bomb load of 4,000 to 6,000 pounds, depending on configuration. It was well armed, with up to 1350 caliber machine guns positioned to defend against attacks from any angle. It was rugged, capable of absorbing battle damage that would destroy lesser aircraft, but it was still a bomber. It cruised at about 180 miles per hour at altitude. It had to fly in formation to mass its defensive firepower, and most importantly, it had to fly straight and level during the bomb run, making it an ideal target for both fighters and flak. German air defense doctrine was straightforward. Fighter units would intercept bomber formations as far from the target as possible, ideally over occupied territory, where German pilots who were shot down could be rescued and returned to duty. The fighters would break up the formations, forcing bombers to scatter, then destroy them individually. Any bombers that survived to reach their targets would be met by dense flak barrages from anti-aircraft batteries positioned around every major German city and industrial complex. The flak defences were formidable. By 1943, Germany had deployed thousands of 88mm guns and lighter anti-aircraft weapons. These guns were coordinated by sophisticated fire control systems using optical rangefinders and, increasingly, radar. The 88mm guns could reach altitudes up to 30,000 feet and could put a shell anywhere within a cylindrical zone several miles in diameter. Dozens of guns firing simultaneously created a barrier of exploding steel that bomber formations had to fly through. What the Germans understood, what their entire air defense system was built upon, was a fundamental limitation of high-altitude bombing. Accuracy was impossible. This wasn't propaganda or wishful thinking. It was physics. At 25,000 feet, a bomber was nearly 5 miles above its target. From that altitude, even on a clear day, a city looked like a map. Individual buildings were difficult to distinguish. Factory complexes blurred together with surrounding neighborhoods. The bombardier, looking through whatever optical sight his aircraft carried, was trying to identify a target the size of several city blocks from a distance where everything looked the same. Wind complicated everything. At high altitude, winds could exceed 100 miles per hour. A bomb dropped from 25,000 feet would take nearly a minute to reach the ground. During that minute, the bomb would be pushed horizontally by wind, drifting away from the intended impact point. Calculating the wind's effect required precise knowledge of wind speed and direction at every altitude between the aircraft and the ground. This information was rarely available and changed constantly. The aircraft itself was not a stable bombing platform. Even in formation, even on a clear day, a B-17 at altitude experienced turbulence, buffeting, and constant small movements. The bombardier had to estimate the exact moment to release, accounting for the aircraft's speed, altitude, and movement. A delay of even a fraction of a second meant the bombs would miss by hundreds of feet. German engineers had studied this problem extensively. Their own bomber force had faced the same limitations. Luftwaffe bombers attacking Britain had scattered their loads across wide areas, hoping that sheer volume of explosives would eventually destroy the intended targets. Precision was achieved only by low-altitude attacks, flying at 3,000 feet or less, where the bombardier could clearly see the target, and where wind drift was minimal. But low altitude meant exposure to light flak and small arms fire that could destroy aircraft. The British had accepted these limitations. RAF Bomber Command under Arthur Harris had adopted a strategy of area bombing, deliberately targeting entire cities rather than specific factories. The reasoning was sound. If precision was impossible, then concentrate. Enough bombers over a large area, and some of the bombs would inevitably hit something valuable. The firestorm raids on Hamburg and other German cities were devastating, but they required hundreds of bombers dropping thousands of tons of explosives across entire urban areas. American doctrine was different. The United States Army Air Forces insisted that strategic bombing meant precision bombing. The theory was that identifying and destroying specific industrial targets, ball-bearing factories, oil refineries, aircraft plants would cripple Germany's war production more effectively than burning cities. But this required accuracy that German observers believed was technically impossible. Oberst Lang, watching the RAF raids night after night, had seen the proof. British bombs fell everywhere except on the targets they were supposedly aimed at. In one raid on Schweinfurt earlier in 1943, RAF bombers had dropped several hundred tons of explosives on the city. The ball-bearing factories, the actual targets, were barely touched. Residential areas were destroyed. Hundreds of civilians died. But the factories continued operating. This was the strategic situation when the Americans began their daylight campaign. German commanders knew the B-17 seconds were coming. They knew the Americans planned to bomb specific industrial targets. They knew the American doctrine emphasized precision. What they didn't know, what they couldn't know until they saw it with their own eyes, was that the Americans had solved the technical problems that made precision bombing possible. The device was called the Norden Bombsight. It had been in development since the 1920s, refined through years of testing and classified so highly that bombardiers trained with it under guard and were sworn to secrecy. German intelligence knew it existed but didn't understand its capabilities. They assumed it was just another optical bombsight, perhaps marginally better than German or British equivalents, but still subject to the same fundamental limitations of distance, wind, and aircraft movement. They were wrong. The Norden was not just an optical sight. It was an analog computer, one of the most sophisticated mechanical calculating devices ever created. And it was about to change strategic bombing in ways that would make German air defences inadequate, despite all their fighters and all their flak guns. The Norden Mark 15 bombsight weighed about 50 pounds and sat in a stabilised mount in the nose of the B-17. It looked like a collection of gears, gyroscopes, and optical elements assembled into a metal housing about the size of a large typewriter. To anyone unfamiliar with its function, it appeared to be just another piece of aircraft equipment. To the bombardiers trained at Albuquerque Army Air Base and later at Midland and Big Spring, Texas, it was the most important technology in the American strategic bombing campaign. The device worked on principles that were revolutionary for their time. At its core The Norden was an analog computer that continuously calculated the bomb's trajectory based on multiple variables. The bombardier would input the aircraft's altitude, which was measured by sensitive altimeters. He would input airspeed, which came from pitot tubes on the aircraft's exterior. He would input the ballistic characteristics of the specific bombs loaded in the bay, including their weight and drag coefficient. Then came the critical element, the automatic drift measurement. The bombardier would look through the optical sight and identify a ground reference point, ideally something distinct like a road intersection or a prominent building. He would keep the crosshairs on this point, and the Norden's gyroscopes and mechanisms would automatically calculate the drift caused by wind. This wasn't an estimate. The sight physically measured how fast the ground reference point moved across the field of view, then calculated the exact wind, drift affecting the bombs. The Norden used this data to solve the bombing problem in real time. As the aircraft approached the target, the bombardier would identify the aiming point, usually the center of the factory complex, or the most critical building within it. He would place the crosshairs on this point and engage the automatic pilot. This was crucial. The Norden wasn't just a sight. It was connected to the aircraft's autopilot system through the pilot direction indicator, a device that gave the bombardier control of the aircraft during the bomb run. For the final minutes before release, the pilot wasn't flying the plane. The bombardier was, through the Norden. The sight made continuous corrections, adjusting the aircraft's heading to account for crosswinds, ensuring that the plane flew the exact course needed to put the bombs on target. The bombardier watched through the optical system as the target moved closer in his field of view. The Norden calculated the precise release point based on altitude, speed, wind, and ballistic data. When the calculations showed the aircraft had reached the exact position where released bombs would follow a ballistic trajectory to the target, the Norden automatically triggered the release. The bombs fell. The entire process, from identifying the target to release, was more precise than anything any other nation possessed. The optical system itself used a magnification of 3 times, later increased to 5 times on improved models. This allowed the bombardier to identify features on the ground that would be invisible to the naked eye from 25,000 feet. Roads became visible lines. Buildings appeared as distinct rectangles. Factory complexes could be distinguished from surrounding residential areas. Training on the Norden was extensive and classified. Bombardiers spent weeks at specialized schools learning to operate the device. They practiced on ground trainers that simulated the view from altitude. They flew practice missions over bombing ranges in the American Southwest, where targets were marked with white circles on the desert floor. The training emphasized not just operation, but maintenance. Bombardiers learned to adjust and calibrate the sight, to compensate for wear in the mechanisms, to keep the gyroscopes spinning properly. Security around the Norden was extraordinary. Bombardiers were told that if their aircraft was shot down over enemy territory, they were to destroy the site before bailing out. Some B-17 seconds carried thermite grenades specifically for this purpose. The devices were removed from aircraft between missions and stored in guarded facilities. Bombardiers signed documents acknowledging that unauthorized disclosure of Norden specifications would result in prosecution. The security measures reflected the device's value. American military planners believed the Norden gave them a decisive advantage in strategic bombing. German and British bombardiers used simpler optical sights that required the bombardier to estimate wind drift and calculate release points manually. Japanese bombing doctrine relied on low-altitude attacks because their sights couldn't achieve accuracy at high altitude. Only the Americans had an automated system that could solve the bombing problem continuously during the approach. The Norden wasn't perfect. It required clear visibility, making it useless in clouds or heavy weather. It required a stable bombing run of several minutes, during which the aircraft flew straight and level, vulnerable to flak and fighters. It required skilled operation and careful maintenance. Gyroscopes could fail, gears could jam. Optical elements could be damaged by flak fragments penetrating the nose. But when conditions were right, when visibility was good and the bombardier was well trained and the mechanisms functioned properly, the Norden could place bombs within a circular error probable of 300 feet from 25,000 feet. That meant half the bombs dropped would fall within a circle 300 feet in radius around the aiming point. The other half would fall farther out, but the distribution was predictable and tight, 300 feet from 5 miles up. To put that in perspective, imagine standing at one end of a football field and throwing a ball that lands somewhere on the field rather than in the parking lot beyond. The Norden made this possible not through human skill alone, but through continuous automated calculation and aircraft control. The mission planners at 8th Air Force Headquarters in High Wycombe had chosen Schweinfurt carefully. Intelligence reports indicated the city's factories produced 52% of Germany's ball bearings. Ball bearings were critical components in almost every piece of military equipment, from tanks to aircraft to artillery. Destroy the ball bearing production, the thinking went, and German war production would slow dramatically. The raid on August 17th, 1943, had been costly. The Americans lost 36 B-17 seconds out of 230 aircraft that reached the target, but reconnaissance photos showed significant damage to the Kugelfischer and VKF plants. The Germans had rushed to repair the facilities and disperse production. By October, the factories were operating again at nearly full capacity. The second Schweinfurt raid, planned for October 14th, would be larger. 291 B-17 seconds would attack the ball-bearing plants. They would fly without fighter escort for most of the route because P-47 Thunderbolts, the longest-range American fighters available, could only escort the bombers to the German border before having to turn back for lack of fuel. The formation took off from bases across England, starting at 1010 hours. They climbed to altitude and formed up into combat boxes, a defensive formation where 18 to 21 aircraft flew in a tight pattern that masked their phalanx. Defensive firepower. Multiple combat boxes formed wings, and multiple wings formed the entire strike force, stretching across miles of sky. Luftwaffe radar picked them up over the English Channel. Fighter units scrambled from bases across Germany and occupied territory. The Germans knew where the Americans were going. The route took the bombers directly toward Schweinfurt. Bf-109 and Fw-190 fighters began hitting the formations near the German border. The fighter attacks continued for over an hour as the bombers penetrated deeper into Germany. The combat reports filed after the mission described waves of fighters, sometimes 30 or 40 aircraft attacking a single combat box. The Germans had concentrated nearly every available fighter in Western Germany for this interception. They came in from the front, from the sides, from above, using cannon and machine guns to tear apart B-17 seconds that strayed from formation. 60 B-17 seconds were shot down before reaching Schweinfurt. More were damaged and forced to turn back. The survivors pressed on. At 1,442 hours, the lead combat boxes began their bomb runs over the target. Flak batteries opened fire, putting up a barrage that filled the sky with black bursts. B-17 seconds held formation despite the explosions, despite the fighters still pressing attacks, despite seeing other bombers falling out of formation trailing smoke and fire. Inside each lead bomber, the bombardier engaged his Norden sight. The process was the same in each aircraft. Identify the ground reference for drift calculation. Wait for the drift measurement to stabilize. Identify the aiming point on the target. Engage the autopilot. Watch through the optics as the target approached. Trust the Norden to make the corrections, to fly the aircraft, to calculate the release point. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The bombs fell in tight patterns. From the ground, German observers saw the explosions march across the factory complexes with mechanical precision. The Kugelfischer plant took direct hits on its main production halls. The VKF facility was struck in the assembly buildings. Other bombs hit machine shops, power stations, and raw material storage. Oberst Lang, who had been ordered to Schweinfurt specifically to observe and report on American bombing accuracy, stood in his observation post and watched with field glasses. He had been in the same position in August. He had seen that raid's damage. He had read the intelligence reports that dismissed American claims of precision as propaganda. The August raid had hit the targets, yes, but German analysts had concluded it was partly luck, that the Americans had simply put enough bombs in the air that some were bound to hit. But this was different. Lang counted the bomb impacts. He noted how they clustered on the factories themselves, not on the surrounding city. He watched as a stick of bombs walked directly down the length of the main Kugelfischer production hall, each explosion evenly spaced, as if someone had measured the distance and placed them deliberately. The young Luftwaffe captain beside him was making notes. "They're hitting from 25,000 feet, the captain said, reading the altitude estimates from the Flak battery commanders. Maybe higher. The rangefinders are showing some formations at 27,000. Lang did the mathematics in his head. 5 miles, perhaps slightly more. Wind at that altitude was strong. He could see it from the smoke rising from the city, blown almost horizontal by upper atmosphere currents. Temperature was well below freezing. The bombardiers in those aircraft would be working in cramped nose compartments, wearing oxygen masks, dealing with cold that froze instruments and numbed hands. And yet the bombs were hitting the targets. The raid lasted 17 minutes over Schweinfurt. When the last combat box finished its run and turned for home, the Germans assessed the damage. Both major ball-bearing plants had been hit extensively. The Kugelfischer facility had taken 31 direct hits on critical production buildings. VKF had sustained damage to approximately 40% of its machine tool inventory. Smaller plants throughout the city had been struck. Fires burned in multiple locations. Lang walked through the Kugelfischer plant that evening, escorted by plant managers and Wehrmacht engineers. The damage was severe. One entire production hall, a building nearly 200 meters long, had been gutted by explosions. The roof had collapsed. Machine tools were buried under rubble. In the next hall, bombs had penetrated through multiple floors, exploding in basement levels where finished bearings were stored. What struck Lang most was the precision of the destruction. The bombs had hit the factory, not the workers' housing across the street, not the church 2 blocks away, not the rail yards on the eastern edge of the city. The factory. The Americans had aimed at specific buildings within the complex and had hit those buildings from an altitude where Lang would have struggled to identify the complex at all without a map. An engineer from the plant walked him through what had happened. We heard the air raid sirens at 1,435 hours. Workers began evacuation to shelters. We saw the formations at very high altitude, much higher than the August raid. The Flak batteries opened fire, but the aircraft continued straight toward us. Then the bombs fell. The engineer paused, looking at the rubble around them. They fell in a pattern, not scattered, not random. You can see it if you look at the impact craters. They're evenly spaced along the length of the building. Someone aimed those bombs at this specific hall. From whatever altitude they were flying at, they identified this building and put their bombs onto it. Lang asked the question he had been avoiding since watching the raid that afternoon. "How is that possible?" The engineer shook his head. "It shouldn't be possible. Our own Luftwaffe can't bomb with that accuracy from 5,000 meters, let alone 8,000. The variables are too complex. Wind drift alone should scatter bombs across hundreds of meters at that altitude. But the Americans are doing it consistently. This is the second time they've hit us. The pattern is the same. Tight groups, centered on the actual targets." They walked through more of the facility. In the machine shop, a bomb had struck the center of the building, destroying precision grinding equipment worth hundreds of thousands of Reichsmarks. In the assembly hall, explosions had demolished bearing inspection stations. In the power plant, a direct hit had destroyed the main turbine. By evening, reports were coming in from other German cities. The Americans had struck other targets that day, using the same tactics, achieving the same disturbing accuracy. Anklam, Marienburg. The raids were smaller than Schweinfurt, but the pattern held. High-altitude formations, tight bomb patterns, hits on the intended targets. Lang returned to his headquarters and wrote his report. He was careful with his language. He documented the damage. He noted the accuracy. He described what he had witnessed. But he also had to address the implications, and this was where the report became difficult to write. The Americans had demonstrated a capability that German doctrine said was impossible. They were bombing with precision from altitudes where German fighters were less effective and flak was less accurate. The Americans were willing to accept heavy losses, 60 B-17 seconds shot down at Schweinfurt alone, to achieve this precision. And most troubling, the Americans had bombers to replace their losses. German intelligence estimates suggested the Americans were producing B-17 seconds at a rate of several hundred per month. The Luftwaffe was shooting down American bombers faster than they had shot down RAF bombers during the Battle of Britain, but the Americans kept coming. Lang concluded his report with an assessment that would have been unthinkable 6 months earlier. The current German air defense system was inadequate. The Luftwaffe needed fighters with longer range to intercept bombers before they reached their targets. Flak defenses needed to be increased around critical industries. Most importantly, Germany needed to disperse its war production, moving critical facilities underground or to locations that were harder to target. His report was one of dozens filed after the Schweinfurt raids. Wehrmacht officers across Germany were reaching similar conclusions. The Americans had solved the technical problem of high-altitude precision bombing. The solution involved technology the Germans didn't fully understand and industrial capacity the Germans couldn't match. The daylight bombing campaign that was supposed to fail, that German doctrine said would fail, was succeeding. The cost to the Americans was enormous. The 8th Air Force lost 60 B-17 seconds at Schweinfurt on October 14th. Another 17 bombers were so badly damaged they were written off after landing in England. 594 aircrew were killed or missing. This was unsustainable by any reasonable military calculation, but the Americans sustained it anyway. What the Germans were only beginning to understand was that American industrial production could replace aircraft faster than the Luftwaffe could shoot them down, and American training programs could replace aircrew faster than the Germans could kill them. The mathematics of attrition favored the side with greater resources. The Norden Bombsight had made precision bombing possible. American industrial might made sustained precision bombing inevitable, regardless of cost. The October 14th raid became known as Black Thursday in American Bomber Command. The loss rate of 20% meant that, statistically, no bomber crew could expect to survive their required 25-mission tour. The 8th Air Force temporarily suspended deep penetration raids into Germany until long-range escort fighters became available. But the suspension was temporary, measured in weeks, not months. By early 1944, P-51 Mustang fighters with drop tanks could escort bombers all the way to Berlin and back. The Americans resumed their daylight campaign with even greater intensity. In February 1944, during what became known as Big Week, the 8th Air Force flew over 3,500 bomber sorties against German aircraft factories. The Norden-equipped bombers struck Messerschmitt plants at Regensburg and Augsburg, Focke-Wulf facilities at Bremen and Oschersleben, and component manufacturers across southern Germany. German production recovered from each raid, but the recovery took longer each time. Factories were dispersed into smaller facilities that were harder to target but less efficient to operate. Critical machine tools were moved underground into caves and tunnels where they were safer, but where working conditions reduced productivity. The ball-bearing industry never returned to its pre-Schweinfurt capacity. Germany imported bearings from Sweden and Switzerland, redesigned equipment to use fewer bearings, and substituted lower-quality bearings in non-critical applications. The psychological impact on German commanders was profound and lasting. Oberst Lang's report from Schweinfurt was filed alongside hundreds of similar assessments from officers across Germany. The pattern was consistent. American bombing accuracy exceeded what German doctrine said was possible. The Luftwaffe was inflicting heavy casualties, but could not stop the raids. Germany's industrial capacity was being systematically destroyed by an enemy who accepted losses that would have broken any other air force. Wehrmacht officers who had believed in 1943 that German air defences would defeat the daylight bombing campaign began writing reports in 1944 that acknowledged defeat was inevitable. The tone of these reports shifted from tactical analysis to fatalistic acceptance. They described what was happening without suggesting how it could be stopped, because increasingly they understood it couldn't be stopped. American material superiority was simply too great. The Luftwaffe fighter force was being ground down by attrition. Experienced pilots who survived multiple combats were eventually killed or captured. Replacement pilots had less training, less experience, and flew against bomber formations that were better escorted and more heavily armed. By mid-1944, the Luftwaffe was losing the air superiority battle over Germany itself. American fighters roamed across German skies, strafing trains and vehicles, attacking airfields, destroying aircraft on the ground. German industry struggled to replace fighter losses. Messerschmitt factories that should have been producing Bf 109 seconds were being bombed by the very enemy the fighters were supposed to stop. The circular problem became unsolvable. Fighters were needed to stop bombers. But building fighters required factories, and factories were being destroyed by bombers. The Norden Bombsight made this vicious cycle possible by ensuring that American bombs hit the factories they were aimed at. Post-war analysis by the United States Strategic Bombing Survey examined the effectiveness of the bombing campaign. The survey team, which included economists and engineers, studied German production records and interviewed German industrial managers. They found that precision bombing of specific targets, particularly oil refineries and transportation infrastructure, had been decisive in crippling German war production by late 1944. The ball-bearing raids at Schweinfurt, while dramatic and costly, had less strategic impact than hoped. Germany found ways to work around the bearing shortage, but the raids demonstrated that precision targeting was viable, and this lesson was applied to more vulnerable targets. Oil production, which couldn't be dispersed or substituted, became the priority target in 1944. Norden-equipped bombers struck synthetic fuel plants at Leuna, Pollitz, and Brux repeatedly. By September 1944, German fuel production had dropped to 18% of its January level. Luftwaffe fighters sat grounded for lack of aviation gasoline. Panzer divisions moved by rail because they had no fuel for road marches. The Norden Bombsight remained classified long after the war ended. Bombardiers who had trained on the device were prohibited from discussing its capabilities in detail. The device itself was studied by other nations, but by the time the technology became available, it was already becoming obsolete. Radar bombing systems and eventually guided missiles would replace optical bomb sights. But during the critical years of 1943 through 1945, the Norden gave American bombers a capability no other nation possessed. The men who operated the Norden paid for its effectiveness with their lives and their psychological well-being. Bombardiers on lead aircraft carried enormous responsibility. The entire combat box followed the lead bombardier's release. If he miscalculated, if the Norden malfunctioned, if he identified the wrong target, dozens of aircraft would drop their bombs on the wrong location. The pressure was immense. Staff Sergeant James Mason, a bombardier with the 303rd Bomb Group, flew his first mission to Schweinfurt on October 14th. He was 22 years old, trained at Midland Army Airfield in Texas, and had been in England for 3 weeks. His pilot was a first lieutenant from Ohio on his 8th mission. Their B-17, named Liberty Bell, was in the lead position of the low element in the 3rd Combat Box. Mason's account, recorded in a debriefing after the mission and later preserved in the 303rd's mission records, described the bomb run in technical detail. He tracked a road intersection for drift calculation. The Norden stabilized after 30 seconds. He identified the aiming point on the Kugelfischer plant's main production hall. He engaged the autopilot, and watched through the optics as flak bursts appeared around the aircraft. The Norden made corrections for crosswind. The target moved closer in the sight. He felt the aircraft shift slightly as the sight commanded heading changes. Then the automatic release triggered. The bombs fell. The aircraft jumped upward, suddenly lighter by 6,000 pounds. Mason looked through the drift sight to observe the impacts. He saw explosions walking across the factory complex. Then he saw a B-17 from another group explode in mid-air, struck by flak. Pieces of the aircraft fell through the formation. He watched another bomber, trailing, fire from its No. 3 engine, fall out of formation, and begin a long spiral toward the ground. He counted 3 parachutes. Mason flew 24 more missions before his tour ended in March 1944. He survived. Many of his training classmates did not. The 303rd Bomb Group lost 7 aircraft at Schweinfurt on October 14th. Each aircraft carried 10 crew members. 70 men from one bomb group, killed or captured in a single mission. The group's casualties for that day exceeded the total casualties of some infantry battalions during entire campaigns. The psychological cost was measured not just in casualties but in the stress of repeated missions. Bomber crew members watched friends die. They saw aircraft explode. They dealt with the knowledge that statistically they probably wouldn't survive their tour. Many developed what was called operational fatigue, a condition that manifested as sleeplessness, anxiety, and inability to function under stress. The Army, Air Forces eventually established rest facilities where combat crew members could spend time away from their bases, but the relief was temporary. For the Germans on the ground, the experience was different but equally traumatic. Factory workers in Schweinfurt, Regensburg, and other targeted cities went to work knowing that American bombers might appear at any time. Air raid sirens became part of daily life. Shelters were built beneath factories and in basements. Workers learned to recognize the sound of approaching bomber formations, the distinctive drone of hundreds of engines at high altitude. The accuracy of American bombing made factory work particularly dangerous. In area bombing raids, the bombs fell across entire cities, and while casualties were heavy, any individual location had a relatively small chance of being hit. But in precision raids, the bombs fell on the factories. Workers who sheltered in place beneath targeted buildings were killed when bombs penetrated multiple floors. Those who evacuated to external shelters sometimes returned to find their workplaces destroyed. German industrial managers faced impossible demands. They were ordered to maintain production despite repeated bombing. They dispersed facilities, moved equipment underground, and implemented night shifts to reduce daytime exposure. But every adaptation reduced efficiency. A factory spread across multiple locations required more workers to transport materials between sites. Underground facilities had poor ventilation and lighting. Night shifts were less productive than day shifts. The accumulated stress affected German industrial output in ways that were difficult to measure but nonetheless real. Absenteeism increased as workers chose not to report to factories that were being targeted. Skilled workers who were killed or injured couldn't be easily replaced. Equipment that was damaged had to be repaired or replaced, using resources that weren't available. The effect was cumulative. A steady degradation of industrial capacity that accelerated through 1944 and into 1945. By the spring of 1945, when Allied armies were crossing the Rhine and advancing into Germany from both east and west, the strategic bombing campaign had achieved its primary objective. German war production had collapsed. Oil refineries stood silent. Aircraft factories were rubble. Transportation infrastructure was destroyed. The Luftwaffe flew sporadic missions with jets and piston engine fighters, but fuel shortages meant most aircraft remained on the ground. Oberst Friedrich Lang, who had watched the October 14th raid from Schweinfurt, survived the war. He was captured by American forces in April 1945 and spent several months in a prisoner of war camp. During his interrogation, he was asked about German assessments of American bombing accuracy. His response, recorded in the interrogation report, was direct. We did not believe this was possible. Our own bombing doctrine said precision from that altitude could not be achieved. When we saw it happening, we knew we had lost the air war. The interrogator pressed him on the Norden specifically. Had German intelligence understood what the Americans possessed? Lang replied that German intelligence had known about an advanced American bombsight, but had assumed it was only marginally better than German equivalents. We thought it was propaganda, he said. The Americans claimed they could hit specific buildings from 8,000 meters. We thought this was exaggeration for morale purposes. We were wrong. The interrogation reports from hundreds of German officers contained similar admissions. The Americans had technological advantages that Germans had not anticipated. The Norden was one. Radar systems were another. The industrial capacity to sustain heavy losses while continuing operations was a third. Together, these advantages had made the daylight bombing campaign successful despite costs that would have stopped any other nation. The Norden bombsight itself was never captured intact by German forces during the war. Shot-down bombers were examined, but bombardiers had destroyed their sites before capture, or the devices had been destroyed in crashes. German engineers who examined photographs and intelligence reports concluded that the device must incorporate gyroscopic stabilization and some form of analog computation, but they never understood the full sophistication of the system. After the war ended, when the Norden specifications were eventually declassified, German engineers who reviewed the technical details expressed surprise at its complexity. The device incorporated technologies that German industry could theoretically have produced but had never combined in the same way. The automatic pilot connection, in particular, was considered innovative. German bombsights required the pilot to fly heading corrections called out by the pilot Korrekses, bombardier. The Norden removed the pilot from the equation during the critical final minutes of the bomb run, eliminating human error in following directions. The legacy of the Norden extended beyond World War II. The principles of automated targeting and guidance systems developed for the bombsight influenced post-war weapons development. Early guided missiles used gyroscopic stabilization similar to the Norden. Inertial navigation systems for aircraft and spacecraft evolved from the same technologies. The concept of automated weapons release based on continuous calculation became standard in modern bombing systems. But the Norden's most important legacy was strategic rather than technical. It demonstrated that precision targeting of industrial infrastructure was viable and, when combined with sufficient resources, decisive. The doctrine of strategic bombing that had been developed in the 1920s and 30s was proven correct, but only because technology advanced to make precision possible. Without the Norden or an equivalent device, strategic bombing would have remained what it was for most nations during the war: area attacks that caused destruction, but couldn't reliably destroy specific targets. The Wehrmacht officers who had stood on observation platforms across Germany, watching American bomber formations pass overhead, watching bombs fall with impossible accuracy, had witnessed a turning point not just in the war but in the nature